So I know the program says kind of it was an interim placeholder title. This is the real title I'm going to go with. So I want to take you from the history of AI models to kind of future work and where things are going, at least where I see things are going. Just as a brief intro, I'm a research scientist at Hugging Face, which is a startup in responsible AI. And I work particularly on evaluating the environmental and societal impacts of AI models and data sets. And two other causes that I volunteer and I'm very involved with is women in machine learning, where we try to highlight the work of women in our community, and Climate Change AI, which is a volunteer org that uses AI to fight climate change. So if you have any questions about any of these things, I'm happy to answer them. So, I mean, you've probably all seen some variation of these headlines. I have a collection. I collect them just because I find them interesting. I've been in AI research for about 10 years now, and the last year has been really weird. Specifically, natural language processing is really my specialty. And so I've spent kind of 10 years doing textual modeling, all sorts of stuff, and the last year has been really different, let's say. And so I want to go back. I want to stop, pause, rewind, and walk you through a little bit of the history of AI models and what we mean when we say generative AI. And so if we had to show the winding road of AI, it kind of officially starts in 1956. That's when the term AI was invented. It was like a summer school where a bunch of really smart people got around the table. They're like, we're going to do artificial intelligence. We're going to make machines that think. About 20 years later, they realized it was harder than they thought. So we had a first AI winter, what we call, in the 70s up to 1980. That's when they realized that all the stuff they sold in the 50s and 60s was a lot harder than they expected, and then funding ran out, and then all that jazz. Then in the 1980s, we had rule-based systems. Actually, even when I started my PhD, a lot of people were doing rule-based, expert-based systems. So that means essentially you write out all the ifs and thens and buts, and then your system will make predictions based on essentially rules that you give it. As you can imagine, that didn't work so well either in the 1980s until 1993. We had a second AI winter when people were like, oh, so you can't just write all the rules for all of everything, right? You can't just formalize it all. This is called symbolic AI, by the way. And then starting in 1993, we have what is, I guess, the third rebirth of AI. We have things like Deep Blue, IBM Watson, when people started believing in AI again, and we saw some pretty big wins, like Deep Blue and like Jeopardy and stuff like that. So we started really to pick up pace again. Starting in 2011, we have what's called deep learning. So it's really we're not going to make any rules anymore. We're just going to make AI models that learn by themselves. And so this is what started. It's still where we are now, but specifically in the last couple of years, we've had generative AI. So this is like the new bend in the road. And I really want to focus on that because I think this is what people have questions about and are interested in. But it's not always very clear what we say when we mean generative AI, right? So just to give you an example, even as recently as a couple of years ago, AI models often were, you would provide them with data. So this is MNIST, which is like one of the iconic AI data sets, essentially handwritten digits and their labels. This was kind of the data set that was used in the 90s, for example, and it's also still used to train systems that will recognize addresses on envelopes. So this was like the thing. It's not that big, but it really gave a lot of the ability to train the first neural networks, the first machine learning models. Then we have something like ImageNet, which is a lot bigger, but it gave us the first computer vision systems. And so Kate Crawford, who spoke this morning, studied ImageNet and all of its flaws and biases and things like that. But they still gave us what's called supervised learning models. And so that means that you have an image, you have a label. This is an orca whale. This is a bus. This is, I don't know. They had some really dodgy labels in ImageNet. But anyways, essentially the model will learn what constitutes something of a certain category. So this is supervised learning. Well, what do we have now? Well, the first generative large language model, at least, is called BERT. It only came out 4 years ago, not that long ago. It was able to predict the next word in a sentence. And so here I prompted it with, my name is Sasha, and I am a mask. So mask is the token it's supposed to predict, the word it's supposed to predict. And the most probable word was vampire, apparently. So it's really predicting based on what it's seen. So I get a lot of vampires or sometimes wrestlers. There's a wrestler named Sasha. Anyway, so this essentially is like, it's like a probabilistic machine that will say, well, based on what you've input it, here's what I predict as the next word. This was kind of the way that language models worked for the last couple of years. Now we have GPT-4, where you can give it a picture of what you have in your fridge and ask it, what are a couple of meals I can make with this, the picture, and it will give you some recipe ideas, right? Magic. So this is called generative modeling. What it means is that it's not like a mapping between an image and a label. It's really producing, it's generating new content. That's what really like defines generative models of any modality. It also generates medical reports. You can there's a couple of models out there. You can upload a radiology report, and it will tell you what the medical condition is, whether there's an edema, et cetera, et cetera. So we're even starting to see really kind of task-specific generative models. And of course, there's a bunch in any kind of application that you can think of. But how are these models built and trained, and is it magic? I think this is important to kind of understand how they're trained, because it's not magic, and it's important to kind of understand the steps that are involved. So recipe of a generative AI model, the first thing is you need a lot of data. We're talking about like the whole of the internet, if you can, essentially is what people use. Sometimes there's some filtering that's done, but a lot of people don't filter, because if you filter, you lose data, right? So any kind of filtering you do, you essentially reduce the quantity of data. So oftentimes it's just kind of as much as you can get. You pre-train a language model. So what does pre-training mean? It's essentially like the BERT example I showed on my previous slide. You're training a model to predict the next word in a sentence. And so essentially what you do is you feed in a chunk of your training data and you ask it to predict the next word. And then essentially if it matches up with what's in the data, you say, oh, good job, gold star +1. And then if it doesn't match what it sees in the data, you kind of penalize it. And that's essentially what happens for millions and billions of times. Essentially, you're training the model to predict what it's seen in the data. And the only reward it's getting is good job or bad job if it didn't predict it, right? So that's what's pre-training. It's been around for 4 years since BERT. Nothing new. What's really new in the last couple of years is this human interaction component that's really made generative AI models shine. Essentially what happens after the model has been pre-trained just on this huge text corpus, you set it up to interact with humans, and the humans will keep training it based on their inputs. And so this is called, if you want to be fancy, reinforcement learning from human feedback. What that means is that humans provide feedback like, this is a recipe for cookies, and then you ask it what's the recipe for muffins, and then you fix the recipe. Oh no, that's too many eggs, that's not enough flour, and then you feed it back into the model, and it gets better. And then you ask it, like write me some script for creating a web page, and then you fix the script, and then essentially hundreds of thousands of hours of reinforcement learning from human feedback, and that's how it gets so good at interacting with humans, because it's learned from humans interacting with it. That's why it mimics us so well. But if we go back into each of these steps, we can really see some kind of inherent flaws that I wanted to hone in on, just so you get a better idea of what each one of these steps entails. So for example, if we hone in on the data, the most common data source for training language models is called the Common Crawl, and Jesse Dodge, who's the next speaker, will talk about what's really in there. But essentially, it's all of the internet. Like, it's a constant scrape of any web page that's out there, and it's updated every couple of months. So we're talking terabytes of data. And so depending on the model that you're training, you want different aspects of that data, right? So if you have a language model, you'll just take the raw text. Just really like you'll remove all the HTML, you'll remove all the links, you'll take the text because that's what you need to train it. If you're using images, you're going to take every JPEG, PNG, you're going to download the image and train your computer vision model. You can imagine what kind of images there are on the internet. I'll leave you to it. If you want to train a multimodal model like GPT-4, you need pairs, right? You need pairs of text and image in order for the system to learn how to generate an image of a cat, for example. And in that way you have alt text on the internet, right, for screen readers and things like that. So you can use the alt text as the label for the image. And so that's how a lot of the text-to-image models are trained. But as you can imagine, all of this content is, sometimes unfiltered, often contains lots of stuff that you don't necessarily want in your model. And then you'll have questions like copyright, right? Like, who owns web content? If I have a website that somewhere at the bottom says copyright Sasha Luccioni 2023, is the Common Crawl going to respect that? How do I verify whether my website's in there? Because honestly, I've tried to work with a Common Crawl, and even to get to it, you have to download 17 terabytes of data, and then once you do, you have to search through that, right? That takes a huge amount of time and infrastructure. And how can we enforce licenses? What if I really don't want my data to be used in that model? Also, which websites are acceptable. It's really interesting because there are like lists of words that people essentially use to filter out. So if the website contains any of these words, we're gonna like filter it out. Some people don't do any filtering. Some people do some. They'll train a model and they'll use that to filter it. Anyway, there's all sorts of stuff, but inherently it means someone's calling the shots, right? And so who calls the shots around which websites are acceptable, and what does that convey in terms of opinions or values? Also, consent, right? This is a big question for artists, musicians who put their work out there. A lot of it is used for training, especially like, for example, image generation models. How can they opt out? How can you say, I don't want any of my images that like have my style, that have my my life's work. I don't want it to be used in this model. Or how do we opt in, saying, okay, I'm okay with these images being used if you, for example, pay me some rights. And so all these questions haven't been answered and essentially are ignored. It's kind of like this gray area, which people just kind of. But we're starting to see lawsuits. We're starting to see people pushing back. We're starting to see artists like actually suing companies, saying, no, I'm not okay with your company training a model that mimics my art. Now, if you move to the second step, pre-training, this is a figure from a paper written by a colleague of mine, Irene Solomon, and this kind of shows you the y-axis, like the vertical axis is the size of language models. Between 2020 and 2022, they've gotten hugely big. It's actually, the way we quantify the size of language models is usually parameters, which are essentially like the little nodes that compose these networks. And so we're talking about hundreds of billions of parameters. So it's gotten pretty huge. What's interesting with this plot is you can also see which ones are accessible and which ones are not accessible. So essentially, anything in red is something that you can only kind of use as a product or as an API, like you can query it a little bit. So this really shows that there's really a monopoly of people who have these models and who they give access to. And so also there are issues of interpretability. Like I can't tell you why Bert predicted vampire. Like I don't know why Bert thinks that my name is Sasha and I'm a vampire. There's no way of retracing the steps, essentially. So interpretability is really complicated, especially since these models are so huge. Like there's no way of like retracing the steps that it used to make these decisions. There's also a lack of documentation. You don't know where these models are, what they're trained on, like what exactly is the data, what are the failure cases. You don't have any of that. You need really expensive hardware to use to run these big models, which means that only a select few companies, organizations, countries can actually host a model and give people access or train a model. We're talking like millions of hours to train one of these models. Like literally, it's pretty ridiculous. And so that means that there's a balance of power issue. And there's a creation of a divide, right? We're seeing more and more a divide between those who have the skills and resources, essentially the money to pay people and compute in order to train one of these models, and those who don't. And if you look at a world map of GPU servers, they're all in the north, right? Even people who, from working in South America, they often have to use a GPU located in North America or in Europe because there's literally no servers that they can use closer to where they're located. And so there's really this like digital divide that's very flagrant in AI right now. Something that I particularly work on a lot is the carbon footprint of AI models. And so we recently did a study and we essentially tried to figure out just how much carbon is emitted when you train one of these like huge language models. And so we calculated like the manufacturing costs, like every time you create like a GPU, which is like a specialized chip for training a model, how much CO2 is emitted. And then if you multiply that by like the 1,000 GPUs that you use to train a model times the million hours and what that adds up to. And we did this for a couple of different models. And sometimes it's 500 tons of CO2 for GPT-3, for example, which is like, it doesn't make any sense, right? Why would you emit like that much CO2 for training a model that will essentially be replaced 6 months later, right? Because then there's GPT 3.5, then there's ChatGPT, and et cetera, et cetera. So we're talking about kind of a ballooning carbon footprint as well, but there's very little data, so you have to kind of do the calculations yourself. And the human interaction aspect, this actually comes up a lot because people aren't aware of how much human interaction goes into training these models because no one talks about it, right? So they're trained for thousands of hours based on human feedback, and who provides this feedback? Crowdsourced workers in places where you can pay them $2 an hour. And so there was a recent Time magazine report about how there's a lot of Kenyan workers, for example, who are paid less than $2 an hour for their interactions with ChatGPT, and how they work 12 to 14 to 16 hours a day, how, of course, obviously their name never gets cited anywhere. When you see a report or a paper or something, you never have the list of people who gave their time and their intelligence, right? Because we talk about machine intelligence, but it's actually imitating human intelligence. And so now we're not only talking about generic crowdsourced workers, like just people who will ask you questions, but also specialized ones, right? Like poets, like programming specialists, because you want, ideally a language model has to cover different modalities, different tasks, and so you want it to be able to write a haiku or write some JavaScript, right? And so in order to do that, you need to hire people who have these skills so that they can train the model. And so we're really creating like this mass of invisible workers, underpaid workers that are also contributing to making these models better without actually getting any credit. And so that's also like one swept under the rug, but a really important thing to keep in mind when you see these magical LLMs, large language models. Think about how many human hours were involved in making them that good. But what can be done? We don't want to be too depressing. I don't want to be too depressing. What can be done, and actually what is being done? Because often, lately I've seen a lot of kind of doom and gloom about superintelligence taking over the world, comparison to nuclear bombs or climate change or whatnot. But there's actually a lot of work that's being done, that has been done, even as far as back as the last decade, around how to make these systems safer, more reliable, more interpretable, et cetera. And just so briefly, the company that I work for, Hugging Face, is kind of a hub for sharing AI models. And so the mission is to democratize good machine learning. But in practice, what that means is that people will train AI models on, translation or image generation or whatever, and they will upload it to the Hugging Face website. And we host the models, and we try to get them to do a better job, essentially. And so I'm going to talk about some of the things we do, just to give you an idea that there are things being done, and it's important to recognize that. So for example, in terms of data and consent. So there's this big data set called LION, 5 billion image and alt text pairs that was created based on the common prawl, right? And most of what people see is like, oh, look, there's pictures of French cats. That's cool, right? That's cute. But actually, there have been reports of medical record photos. So there's actually images of people without consent in this data set. And so obviously, huge issues, but like what can be done, right? And so for example, we're working to create data sourcing reports so that when someone sees a data set, LION is a bit particular because it's so big, but often, for example, 42 million images, you can see how many of them actually people opted out. Like, so people can go and be like, I don't want, like, I found my images in this data set, I don't want them there, and then that gets tallied to like this data sourcing report. And so for example, if you work for an organization that is worried about legal ramifications, you can actually go and pick a data set that is respecting people's consent. And so this is going to be important because data sets are being created all the time, and it's important to have this kind of these mechanisms for documenting sources and consent. Another aspect that I work on that I think is really, really important is understanding and data sets, because like now we're talking about data sets that are so big that people just kind of like, they're like, well, it's the internet. We're gonna train on the internet, but it's really important to understand what's in there because it helps us understand what the models will produce later, right? Because if your model is being like toxic and producing hate speech, it didn't learn that from the air. It came from somewhere, right? So at Hugging Face, we were making tools for investigating data sets. So for example, we have a tool called Data Measurements Tool, which essentially you upload your data set or you pick an existing one, and it will find you duplicates, low quality, this is for textual data, low quality examples. It'll find you like anomalies, it'll find you metadata, it'll find you kind of all sorts of things that you can look at to figure out what the data set contains, essentially. Like, so for example, there's duplicates actually are a big deal, because if you have a lot of duplicates in your data set, it's probably not good quality, right? So we did that, and we also have some medical data sets that are up on Hugging Face that people uploaded, and they could be useful to know, for example, in this Med MCQA data set, which is medical question answering, what is the distribution of patient ages? You can do the same thing for genders, you can do it for geographical locations, and so essentially, when you want to use this data set, you want to know like how many adults are there, how many children are there. And so like we create tools like this so that people, before like just downloading a data set, so you know a little bit more about it. In terms of model access and documentation, so imagine you're looking for a data set that will do, I don't know, German to English translation because you want to create a robot that people can talk to in either language. You go to the Hugging Face Hub, there's so many models that do English to German translation. How do you pick? And so essentially, we have all open source models, so because people can build upon them, and that's really important because often, for example, if you're doing a medical robot that will work in a hospital, it's important for it to know medical terminology, which is not something that's by default in a machine translation model. So often if you take one of the models, you can continue training it on your own data. You can be like, well, I wanted to know exactly like the special terms in German and English for my robot. It can also help us understand what the model's behavior is. So for example, if we look at kind of models, language models that were released recently, maybe you've heard about some of them, like Llama, like Bard, like ChatGPT. We're really seeing this like incremental improvement. But also what we see is that the models in gray are actually the open source ones, and they're actually catching up to the proprietary, closed source, kind of secretive models. And so we're seeing that that open source is a viable option, especially if you want models that are not a one-size-fits-all solution, because often, for example, ChatGPT, there's one ChatGPT no matter who queries it. It's not going to represent necessarily like specific use cases, specific vocabularies. It's like a foundation quote-unquote model. But with open source models, you can create different versions, and that can be really important, especially if you have specialty kind of more niche applications. And it's great to see that there are many labs and organizations doing open source research. And so I worked on a project that's called Big Science. And essentially, we modeled it after the CERN kind of Hadron Collider. And so we brought together over 1,000 researchers across the world. And we trained the first, I mean, this was a whole year ago. So this was the first open source large language model of 176 billion parameters. And it was kind of the first one that proved that it didn't have to be only big tech companies that can train large language models. And so people are also using this as a kind of as a guidebook. So people are doing their own big science initiatives now, kind of derivatives in different modalities, for text, for image, for multimodal. And so it's kind of interesting to see that people are coming together because even, especially people who don't have access to like large computers are really keen to participate in these projects because it helps them learn and helps them get skills that they couldn't get just because they don't have 1,000 GPUs lying around, right? So very few people do. And also, when you're picking models, in order to know what's in there, model cards and guidelines are really important. And so, for example, at Hugging Face, we have templates that people can use. So each time you upload a model, it like prompts you. The website tells you, fill out this model card. And so it asks you to document its risks, to say what it was trained on, how it was evaluated, what the environmental impact is. I added that one. What the citation is. If someone uses this model, well, how can they cite, your org? How to get started, how to, I don't know, how to download the model and things like that. So essentially, we ask people to create like an instruction manual for their models because otherwise, like, you don't know what it was meant to be used for, and so people can misuse it just by not knowing. It's not because they wanted to explicitly misuse a model, just because the more information you have, like you can be like, this is not meant to be used in, medical, in education, and things like that, like high-risk cases, essentially. And I also recently helped push through a code of ethics for our biggest conference. It's called NeurIPS, which is the Neural Information Processing System Conference. It's been around for like 20 years. And until this year, it didn't have a code of ethics. And so people could use any kind of data, not disclose anything about the data or the model. And so starting this year, a very big thing, people need to disclose where their data is coming from, how they trained the model, how they evaluated the model, all this stuff that seems kind of like it seems kind of obvious, but that wasn't being done. So now, like for example, if you use crowdsourced work, if you use crowdsourced workers in gathering or labeling data, you have to declare it. You have to declare how many workers, how much they were paid, et cetera, in order for the invisible labor that goes into machine learning models doesn't get overlooked. And same thing for carbon emissions. You have to report those too. And so a final thing I want to cover is evaluating generative models. So for example, if you think back to the GPT-4 example and it gives you a couple of recipes, there's not really a good way of saying like, this is a good recipe, this is a bad recipe, because everyone has their own chocolate chip cookie recipe, right? So this is really, really hard. There's no single answer for evaluating generative models. That's why people don't do it, because they're like, oh yeah, well, here's the model. I can't really tell you how good it is, but trust me, because there's no single way of doing it. And so there's no single answer, there's no evaluation data sets, there's no access to underlying models. Say you wanted to evaluate ChatGPT, like how would you even do it, right? So this is like my favorite kind of metaphor. I came up with it spontaneously. Now people are using it in discourse. ChatGPT could be 3 raccoons in a trench coat, and we wouldn't know, because like we're querying a black box and it's giving us answers, but we really don't know what it has under the hood, and that's a problem when you want to evaluate a generative model. And so what we're doing in the open source community is we're creating open source tools. So this one is to understand text to image models, right? Like depending on what you query it with, you can compare different models. So for example, this is the prompt gentle CEO, and you can see that it's all smiling kind of white people in glasses. If you do, angry janitor, it's not going to be the same images of people. Let me tell you that. And so we're creating tools that people can use, and essentially like you enter a couple of prompts, and it compares the images from different models and tells you what you can look at the images and kind of make your own ideas about them. We also have average faces. So once again, 3 different models: Stable Diffusion 1, 2, and DALL-E. And it, like for example, if you prompt janitor, it's really not the same images that are getting generated, and it really reflects the training data it was trained on. So DALL-E, for some reason, predominantly white people, and it's really surprising. But this is only something you can discover by playing with the model. And also, if you query identity groups, anything with like people of color, even like, for example, Native Americans, it will like spit out cultural stereotypes by default. It's really quite surprising. And so things like this, like kind of prompting the model, auditing the model are really important to understanding, because there's no way of evaluating them. How would you give this a score, right? Like, yeah, this one is more racist than that one, but that's about it. It's all kind of relative. Just as a closing slide, it's really, I feel that the AI coverage in the news lately has been mostly very monopolized, very kind of existential risk. We call this X risk, because people have been insisting, on the risks to humanity, the superhuman intelligence, the stuff like that. But you have to kind of keep in mind that AI belongs to everyone. It's not a single kind of, there's no person or organization that owns it. Even if currently ChatGPT is the thing, tomorrow it could be something else. And so there's a lot more diversity in AI research than what you hear about in the news. And so there's a lot more people who are working on very kind of proactive, very transparent, very responsible, I guess, somewhere initiatives. And it's important to keep that in mind when you hear ChatGPT every day in the news. And so part of our work is also making these less visible applications more visible. And so to promote like more research from different communities, more accessible research, more interpretable research, in order to kind of vary the narrative a little bit, and to also give people tools, right? So if you do want to use AI models, even if they're closed source, how can you evaluate them? And so that's kind of part of my work. And it's interesting because this is going to sound cliche, but it's not only from a research perspective that these efforts are important, but also because AI has to be diverse. Because like last week I was talking to some people from the Ministry of Education in Canada, and they were saying, oh, is ChatGPT going to replace teachers? And I was like, there's no way ChatGPT or any generative AI model can replace a teacher, because there's so much diversity in teaching. It's not just answering questions, it's empathy, it's psychological stuff. There's a lot more to it than that. And also, can you think of the different cultures, the different languages, the different realities that we operate in? And so you can't just take any single AI model, no matter how good it is, and expect it to replace all teachers, even in Canada or all over the world. And so, I mean, if I wanted to end on this note, that AI belongs to everyone, and it's much more diverse than you might think it is. And so there's things that can be done and that continue to be done in order to make it more accessible. Thank you. No mic?
Thank you so much, Sasha. While we switch over, we have time for maybe one question. One question. Maybe I'm wrong.
Yeah.
not familiar with AI at all, but so I understand that there's things which are undesirable to be in these data sets for these models, so you don't get these toxic models. So is it common or regular for these things, rather than removing these from the data set originally, to have employ people to take these toxic results out? And what's the motivation behind that?
It's because it's so hard to do. It's so hard to filter data. Jesse will talk about that meaningfully, because it's like you can't just use keywords, because just because something contains a certain word doesn't mean it's toxic, or vice versa. It can be very subtly toxic, and so that's why crowdsourced workers are mostly employed. And also they have now like filters on model outputs. So because it's so hard to filter the data, they'll filter the outputs, and so like once GPT-4 generates something, it's going to be checked for toxicity. It's going to be checked for like hate speech and racism, and if it doesn't meet the bar, the score, it's going to get filtered out. And so there's also like post-processing things that are done, because it's such a tricky problem. It's just really, really hard, and there's no good solution for it, I think. But yeah, Jesse will talk about solutions.
Thank you so much. Jesse, over to you.
Hello, everyone. Working? OK, there we go. Hello, everyone. Thank you for having me. My name is Jesse Dodge. I'm a research scientist at the Allen Institute for AI, which is just down the street from here. I work on the Allen NLP team. I assume my slides will show up at some point. And I work on a lot of things. I'll keep talking until my slides show up, I guess. That's fine. There we go. So I work on a lot of things. Today, I'm just going to focus on a few of them. I like having questions in my talks. I see we haven't had many questions during the presentation, but if anyone has any questions during my talk about something that's on the slide, raise your hand, speak up. I enjoy interacting and making it more a discussion. And then also, hopefully, there'll be time for questions at the end. OK. The field of AI has seen remarkable progress on a broad range of tasks in recent years, partially driven by increasingly large models trained on increasingly large data sets. So here in this plot, we can see the number of parameters for some large language models that were released a few years ago. I took this plot from a Microsoft blog post from 2020, but of course, this trend has not slowed down, right? Models like GPT-3 are, in fact, way off this scale. And models like GPT-4, which just came out recently, we assume are off this scale, but we don't know because they're not transparent. We'll come back to that idea. A couple years ago, we were naming a lot of our models based on Sesame Street characters. And so images like this ended up on Twitter and in social circles a lot, sort of indicating that we really are boiling the ocean just to make our AI systems work. So as I said, that plot was from a couple years ago. More recent work has shown, in fact, this trend is continuing. Here on the y-axis, we have the number of flops that are used to train some large AI systems. This is roughly the amount of compute. That is a log scale. So any linear line you see on here is, again, sort of dramatically increasing, exponentially increasing. And according to some of these estimates that were presented in this paper, the doubling time for the amount of compute that are put into our AI systems has varied from somewhere between every 4 months to about every 2 years. They argued that today, we have about a 10-month doubling period. So every 10 months, the computational cost of our large AI systems doubles. That's the current estimate. And I'll remind you, maybe some of you know this, Moore's law, which estimates the number of transistors on a chip, states that roughly computational power doubles every 2.2 years. So here in the field of AI, we are far outpacing the pace at which the hardware and the other technology can keep up. So we are pouring more and more resources into AI at a faster rate than even other fields of technology. And I just happened to see this tweet the other day. The tweet says there's a new book coming out, and the title of that book is Training Large Language Models, and the subtitle is It Hungers, and it has this Lovecraftian monster on the cover, sort of, again, indicating that we're still in this era of increasing scale and compute and cost. So those two papers are from the past couple years. We noticed this trend back in 2019. We argued that this increase in computational cost has really two implications that we should concern ourselves with. This work, we were fortunate and we got a good amount of press. And so these two different press articles highlight these two implications quite nicely. So the first from the New York Times is that there was worry about a concentration of power. And again, this came out back in 2019, and that has really only accelerated. And again, we'll talk about that more. And that at some point, now that we are pouring all of these resources into these AI systems, that we really do need to consider the climate impact of our work. And Sasha, who just spoke, is a leading voice in that field. So these are going to be two themes that come up throughout my talk. I've got three different topics. So on the left here, this is sort of the outline of my talk. These are the three things I'll discuss. And these themes on the right about the concentration of power and the climate impact will come up and shape our discussion. OK. So diving right in, first we're going to talk about web-scale datasets. And actually, I have to say, this has been a phenomenal set of presentations today. Normally, when I'm invited to speak, I'm the only one talking about web-scale datasets. And I'm so happy to see all of the people. We've talked about it a lot already today. So yes, with ever larger computational budgets, we are turning to ever larger datasets. These data sets are so big that we absolutely cannot look at all of the examples. I've seen some estimates about how long it would take to read the text in some of the data sets. Earlier, we saw how long it would take to look at all of the images in the Lion data set, right? These are far larger than a person can actually deal with. One of the largest sources of text is the internet itself. Here, one common paradigm that has emerged is taking a scrape of the web, for example, from Common Crawl, and applying filters to it with the intention of retaining high-quality natural English. And a common idea that comes up is that if you start with enough data, you take all of the internet, and you try to filter out things that aren't actual text written by people for people, then you'll end up with something that is somehow representative of English. But of course, we know that's not the case, right? This is inherently biased data. It's only going to represent text that the text of people who had access to the internet, right? They had to have time to write that text. So here, this process is what's driving of taking the internet and filtering it and then training on this sort of representative English. This is what's driving advancements in large language models and has been for a few years. So we provided some of the first documentation of a data set created in this way, the C4 data set. But what I hope you take away from my talk is not so much about that particular data set. Instead, it's about community-wide issues that arise from this procedure. So we released this paper back in 2021, I believe. It was a couple years ago now. We argued for 3 levels of documentation. The first being just documenting the provenance of the data. Where on the internet is this text scraped from? Then providing some information about what's included and some about what filters were applied, so what data is excluded. Here, again, I'll highlight this is a massive data set. When I say there are 365 million documents here, one document, it contains the text scraped from one website. Right? So imagine trying to read 365 million websites. You couldn't. But that's what these models are trained on. So some of our documentation here contains some surprising information. Right? We see this on the right is a plot of the websites that contribute the most text in this data set. They're ranked. So near the top, we've got Wikipedia. We've got the New York Times. Interestingly, the #1 source of tokens in this data set is patent text, right? This is super unexpected. There's also things like scientific articles. Anything that ends up on the web is going to end up in one of these data sets. And I hope that that sparks something in your mind where you're like, oh, the internet contains a lot of things that I probably wouldn't use to train a model. I encourage you guys, again, this is a relatively short talk. There's a lot more analyses in our paper. One important one that I'll just mention is an analysis of the identities that are included or excluded. And we found that people that speak dialects of English that are not European American English are systematically excluded from these data sets. And therefore, the technologies and the benefits of these large language models don't work well for people that speak any dialect of English other than European American English, right? So I encourage you to check out the paper for some more detail. At the Allen Institute, where I work, we also have a project working on AI literacy. We believe it's more important than ever to help educate people on how to use these systems. Earlier on the panel, we heard discussion of hallucinations, for example. We heard discussions of appropriate uses for language models and situations where it's probably more appropriate to use other tools. So as a part of that project, we partnered with the Washington Post. Some of you may have seen this. I think this article came out about a month ago, to help teach people about the contents of these data sets. So the models, as we've heard, Sasha just mentioned this, the models themselves are inscrutable. We don't always know why a model generates a particular string, why it says a particular thing, right? The best thing that we can do is understand the data. And so I'll just briefly read this quote here. It says, "This text is the AI's main source of information about the world as it's being built, and it influences how it responds to users. If it aces the law school admissions test, for example, it's probably because its training data included thousands of LSAT practice sites." And I'll also highlight just this visualization. They had a great visualization, much better than in our paper. So if you want to read something a little more visually pleasing, check out this article. Here, they highlighted just a few sources of text. So they've got the New York Times, which we already saw. They also have RT.com, which they described as a Russian state-backed propaganda site, and Breitbart, which is a well-known opinion and far-right media site here in the US. This is what's being used to train our language models, right? Unfortunately, this kind of documentation takes a lot of effort. It's taken a lot of us, even just working with them on this piece, it took the better part of a year. And there's a number of engineers on our side. These journalists were also working with engineers on their side. So it is logistically challenging, but we have some insight into what these models are being trained on. So the C4 data set, as I mentioned, came out a couple years ago. The field is moving so fast. The llama models were released recently by Meta, I think just a month or two ago. Here you can see, while they didn't provide any information about the contents of the data sets, they did provide this small table about where they were sourced. So here you can see this, the C4 data set, which we were just talking about. It makes up 15% of their training data. So their models trained on 6 times more data than models were a couple years ago. And where it says common crawl there, that again is web scrape data. So now they're really reaching to every corner of the internet to try to get as much, people's personal blogs, any news site that they can, any text that's available online. That's what they're going for. Also, I will highlight, again, this is sort of one of our themes of this talk. GPT-4 was just released, I think in February or March. This article highlights nicely something that many of us have been saying, which is that GPT-4 is closed source. We don't have access to the model, and they are purposefully not telling us any information about what it was trained on. They're treating that as a competitive advantage. Yeah, there's a question.
Are the social media sites also part of it? So Facebook?
Yeah, so the question is, are social media sites a part of these web scrape data sets? So for the public ones, often they're not. So it was mentioned earlier that there are things you can do. Like when you create a website, there's a file called robots.txt, and you can ask that web crawlers don't crawl your website. It is not guaranteed. There are lots of other things people try to do. They say in text, if you use text from this website, please attribute us. That doesn't happen. If please don't, if you put on your website, please don't use information from this website to train a model, that is completely ignored because that is not the standard way to prevent people from doing so. So there's, the large tech companies are under no obligation to do that, and they won't. Yes. So here, what we can see is we know that these models are being trained on massive crawls of the web, but we don't have access to that data. This trend is continuing. So PaLM 2 came out, I think, last week. In the PaLM 2 paper, it was 91 pages, and they said repeatedly, I've taken this quote from the conclusion, it says, we find that the data mixture is a critical component of the final model. And they provided almost no information about the contents of their data set. They're viewing it as a competitive advantage. So here, we are at a pivotal moment in the history of AI. The trend for large for-profit companies to be less and less transparent with every release means that work from institutions like the Gates Foundation and other open source operations are more important than ever. Here, you can see as time goes on, models are being released less frequently. You only have access to play with them through an API, for example. And data sets, not only are they not being released, they're not being documented, and less information is being presented. Today, we can guess what the next steps are going to be. They're going to fix the problems with the models that we've seen, right? So we can guess what the immediate next step is going to be. But then any advancements that they make, that closed source proprietary organizations make, are not going to be public, and they're only going to benefit those companies. So in the future, we won't be able to know what they're doing. So I'm arguing here that open source will continue to work in parallel, and these large for-profit organizations will continue to benefit from the open source community, but they will necessarily diverge. At the Allen Institute, we have a number of projects where we're aiming to increase transparency around these large data sets. We're doing what we can to help forward the mission of open source. So C4 is that data set at the top. We are providing some of the first documentation across different data sets that were used for training these large models. Here at the bottom, you can see the Lion data set. That's come up a number of times today. This requires some significant engineering efforts, but showing things like the number of tokens per document, which is basically for each website that you're scraping text from, how much text do you get, for example, and these data sets have significant differences. I care a lot about the science of artificial intelligence and using AI for science, and so understanding even simple statistics about how we're training these models, like this is the path for improving what we're doing. And so earlier, it was quite interesting to me, in a presentation this morning, we saw the sources in the Lion data set that provided the most images. Here, we're showing the sources that provide the most text. This data set is, of course, driving models like Midjourney. It's in the press quite a bit. What you can see, the largest sources of text here are Shopify, eBay, Amazon, et cetera, right? So descriptions of images from those sources are rich and contain a lot of information. I expect once, this project, I should say, is ongoing work. It's a work in progress. We have not published this yet. Once we do, I expect that information will be used to sort of iterate and improve on these data sets. We also, as a nonprofit, work with other organizations to help release their data set. So C4 originally was created by researchers at Google. They were unable to release their data. And so as a nonprofit, we were able to reproduce it using code that they gave us and then publicly release it and critique it. I think this is a vital sort of piece in the AI research community. Those that can't, for legal reasons or whatever, release their data, we can act as a sort of intermediary to help get that data public so that it can be critiqued. If the closed source community stays fully closed source, we don't know what they're doing. We can't describe the harms. We've done this with C4, a multilingual version of C4, Meta's No Language Left Behind project from last year. That was a big push for them. We released their data. We also released the workshop on machine translation shared task on African languages last year. We released their data. So we act as sort of a hub. We've gotten some nice press about this too, which is quite nice. And what I will say, something actionable for the people in this room is if you have an application or you've got a large amount of data, let us know, and we can work on helping you get that data to be public and then helping other people to sort of train on that data. If you're looking at all of these presentations today and saying, like, how do I get my application to be something that AI researchers care about, it's through the data. It is by creating a large corpus, as big as you can get, having as much data as you can, and then saying, hey, AI researchers, here is a nice curated data set that people actually care about. That is gold to AI researchers. We would love that, and we will absolutely take that and just train models on it. I'll also highlight one other project. So we just announced last week that we are training a large language model. It's called OLMO, which stands for Open Language Model. And here, again, we care a lot about the science of AI and AI for science. So we view this as a platform. We are purposefully being open and transparent and inviting critique. We're trying to reproduce what other people have done, but doing it in a way that enables people to say, hey, here are some harms, ethical harms that you're missing, or here's a way to process your data that leads to better results, something like that. So again, if you guys have data or applications, let us know. OK, so that was the part of my talk on web-scale data sets. Next, I'll just briefly talk about climate change and some other things going on at my company. So of course, we've got this increasing scale of data and models. We also have just the number of research projects are growing. I'll move pretty quickly through this. Here, we know that about 1% of global electricity demand is in data centers today, and that's where all these models are run. And so I'm going to talk about some work last year where we partnered with Microsoft Azure on measuring the CO2 emissions from training some common AI workloads. First, we take pieces of the hardware and actually measure their electricity consumption. This is a time series represented here on this plot that I found online that's not actually a time series. Then we measure region-specific emissions. So this depends on where in the world you're located. We then estimate the emissions for that electricity consumption in that region at the time that it was consumed. This is the key component. And on the next slide, I'll show you the key idea here is that we're estimating emissions for AI workloads in different regions so you can decide what region you want to run your workload in. So here, this is a plot we use to answer two questions. One, does the amount of CO2 emissions vary by the time of year? And the answer to that is yes, but not that much, which is good, because you can't always decide what time of year you're going to run your AI workload. And two, does the amount of CO2 emissions vary as you change the region that you're running your AI workload in? And the answer there is yes, with the most efficient region having about 1/3 of the emissions as the least efficient region. Here, this is the same information. Yes, this is the slide I usually pause on. So here, this is the same information as on the previous slide, but just showing a range of different models. At the top here, this is training a model that's about 1/10 the size of a model like GPT-3, and it's trained for about 1/10 the duration. So imagine GPT-3 would be like 2 orders of magnitude larger here. My takeaway here, for some of these small models, they release about the same emissions as training a phone or charging a phone. At that stage, we don't expect people to buy carbon offsets or report, the CO2 emissions from their electricity consumption. But when your actions are releasing the same amount of CO2 emissions as burning a rail car full of coal, at some point, the responsibility lies with you to report the emissions of your actions and to take steps to try to mitigate those harms. Was there a question? Yeah, OK. Great. So again, I would encourage you to check out our paper for more. We did have some nice press on this as well. This is a collaboration with Sasha, who happens to be here in the front row. Yes?
Can we compare with other industries though?
Can we compare with other industries?
Yeah,
yes.
This is unfair kind of to something else that doesn't have carbon payoff or whatever. But I mean, just the absolute amount is not always
Yeah.
the absolute amount.
The absolute amount of emissions isn't always a great metric.
Yeah, because it's relative. You want to compare to something else. I mean, I get the house is nice, but what about other industry if you take something? Like that's a fair comparison and say, okay, are they paying
Yeah.
their contributions or whatever?
Sure.
Right?
Yeah. I think the industry around CO2 emissions is young. Trying to buy offsets, for example, is a notoriously difficult process. I'm not sure that I would say if other industries aren't doing it, that means it's fine and we don't have to. That's not what I would say. I would say, transparency is step one. Like, we have to be transparent about what we're doing. Then we can make informed decisions. Do we buy offsets? Do we do whatever? Transparency doesn't cost us anything, also. I think it makes us look good. Some people don't think it makes them look good. But I encourage everyone to be as transparent as possible here. Yeah. Does that answer your question? I mean, it's a little hard to say, like, how does this compare? We can say how this compares to, like, flights or something like that. Yeah, if that's a relevant thing. Yeah.
Compared to Delta and its work, etc.
Sure.
And then this is what they're doing. Like, it has to have another scale of another industry. Having just one scale that you add for houses is unfair.
Well, I don't know. I mean, it really depends on the industry that you want to compare against. Of course, if you want to compare against the energy and gas industry, it's going to look different than something like flights. Also, I will just say again that this is the sort of lower bound on what these emissions are. We're not capturing a lot of other things. Yeah. OK. I will just briefly then, we're basically at the end of my talk, so I will briefly say at the Allen Institute, we work on many things. One question when I talk about CO2 emissions is like, is this, are emissions from AI going to destroy the world? And the answer is today, no, but unless we start tracking these things now, it can quickly get out of hand. At the Allen Institute, we also care about other things. Semantic Scholar is a website which has what I believe is the largest collection of scientific documents in the world, and we want to accelerate the process of scientific discovery using artificial intelligence. If we care about concrete, so maybe this is a good example. If you look at the largest sources of emissions, concrete emits about 8% of global emissions today. We hope that through accelerating the process of scientific discovery, we can get that rate down. We also have a number of teams working on AI for the environment. So Earth Ranger focuses on providing information to ecologists and biologists that help them track relevant information for themselves. Skylight works on mitigating illegal fishing. And we have a team directly working on climate modeling. We are about 200 people. And we also, of course, work primarily in AI. And so we have teams working on everything from computer vision to natural language processing to moral reasoning, et cetera. And that is the end of my talk. Thank you.
Fantastic. Thank you so much. I think we have time for 2 questions while we switch out computers.
Hiya. I was just wondering, in terms of the responsibility for reporting the emissions, so these this is mostly from the electricity generated, from what I understand, right? So it's probably routinely captured in what countries already have to report to the UN and so on. Is this detectable yet in terms of like, when we look at things like historically 8% has been concrete production and 30%, I don't know, I can't remember all the data,
Yes.
but can you already see a shift in terms of electricity taking up a bigger share of those pies?
Yes, absolutely. And especially, so now, as I mentioned, the whole theme of my talk was like this increasing scale is leading to more and more consumption. Now, we know that today about 1% of global electricity demand is through data centers. By 2030, the most optimistic estimations are that it's going to be about 7%. And the expected estimates are that it'll be about 20%, right?
Wow.
So there's tremendous growth in data centers. As you can imagine, tremendous money is being poured into these systems, and they require hardware to run. So being transparent about that now sets us up for the future. If we don't do that now, I think these, of course, the way the capitalist system works is they will do their best to prevent, the need to be transparent around something they might have to offset.
Great,
Yeah.
thanks so much.
Fantastic. Thank you.
Thank you. While this is setting up, yeah.
I think we're all set
Maybe I'll
up.
come over here.
Yeah. Thank you so much. Our last speaker of the day, I hand it over to you.
Hello, can you hear me? Good. Yeah, so I don't know what to say. Everything has been said, but I was given a title, but I might not go in the specificity of what is being said. But I just wanted to. I don't have an outline because I have to remove the outline based on what being discussed so far. So I need to change the way I wanted to talk. And just I wanted to give a brief outline of where I come from, and then you could start seeing a couple of comments I make can cross-reference from a different perspective. By background, I'm a computer scientist. I'm an IBM distinguished engineer, and I have been in a number of industries so far, and from the use case perspective, but looking at the core of the technology. And just to give you a sense of the, somebody mentioned education versus these language models, etc. I think sometimes we really make statements that are undermining the specific domain modalities, that education is not like question and answer, it's really knowledge acquisition, right? And knowledge acquisition comes through time, comes through wealth of expertise, experiences that you learn, acquire over a period of time, then you gain skills, right? So it's a learning process, a journey, and incorporating that knowledge is into language models or these larger models is really quite unthinkable in a way that how many billion people we have in this world, and every person, the way they learn, the way they engage in tracked learning and acquiring knowledge is different, right? So most of you relate that one. And then you go in the mobility, traffic, supply chain, agriculture, climate change, et cetera, things are really becoming interesting and complex. And I happen to work in many of these over a period of time. And when that inflection comes in, we start looking at this foundation model, generative models from different industries' perspective, the really interesting things start emerging, but we are talking about one sort of modalities. And I just wanted to give you some perspective as I go, and they can see where I'm coming from. So we have been working with the GATE Foundation for a couple of years now, looking at digital health from a number of perspectives, looking really understanding how really the public health change over time using data and analytics to really help inform decision making. And the way we're really approaching it really from 4 principles perspective, really, how do you actually utilize these techniques in a more innovative way? And the most important thing is really co-creating with the local community. That really, today what we see, basically crowdsourcing labelers, right? So how do you embed them within the knowledge creation, model creation, and insight creation pipeline as a workflow? They become part of really this creation of this context-relevant models and etc. So just if I zoom down a little bit, this is what we started first, right? How do you really start bringing these techniques and these models, these algorithms into decision-making, for example, these interventions, right? And then how do you actually use these models into really start understanding, characterizing the population and across a number of domains to really start quantifying and also helping making decisions and being part of the clinical decision making using techniques from what we learned from AI, and now it goes on and on, right? So just if you zoom down the first one, it's, as most of you know, malaria is one of the most endemic problems that we are suffering for centuries across the continent of Africa, in particular if you look at low-income, low and middle-income countries, you start seeing the stunning numbers still remains the same, right? So we have been working on across a number of advanced epidemiological modeling, simulation models, start incorporating AI, start bringing a hybrid approach using AI and simulation kind of interplay together. We start seeing these all sort of things, but still we have the challenge, we're struggling. And how do you really, I have a couple of colleagues that they have worked on this domain, and start actually interrogating these models, simulation, particularly deeply using AI, to start bringing the aspect of what we say reinforcement learning and other AI techniques to how do you really make decisions? How do you enable this fast and efficient way of arriving to some conclusion that helps in the decision-making processes in the models? And then you start seeing a lot of these issues like becoming suboptimal and sub-regional, sort of territorial, right? Everybody has his own bespoke models from left and right. Within one country, you'll find several hundred bespoke models, and they don't even interoperate together. They don't work on the same data modalities and model. And you start seeing all these kind of things. Even if you bring AI to start actually ensembling or interrogating across all these modeling agents, but still you have a problem because you have to optimize, you have to make decisions, et cetera, et cetera. So this is really, at present, there is no solution that we start seeing that provide actually these policymakers with really sort of kind of navigable methods that helps them to make informed decisions. And especially you make decisions or you make policies after things have happened, right? So a lot of the time, by the time you make policies, things moved. So you are making 2022, you make decisions for 2021. So that's, again, consistent in diseases, in education, policy making, et cetera, et cetera. And again, we have seen also in climate change as well. So, and I have that some techniques already exist. You can integrate, you go on and on and on, right? So if you come even to second narratives, looking at, for example, sort of what we know from neonatal problems, and when we see family planning problems, we start understanding, question, asking, how is it really sort of family planning sense? How the transition from one method to another method happens? What triggers that one? What happened? Why? These are questions typically we do through surveys, through encounters, and how they are effective really themselves. And we start seeing also from an MNSH perspective, how do you really certify these kind of things and help really making the right decisions? Where is the AI? Where is the knowledge, the language models? You start asking these kind of questions. Really, now you can start asking a question in even the family planning things: when, who, what, why? Can you ask ChatGPT? Can you ask? So I'm just trying to give a sense we are sometimes underestimating the magnitude of the problem and the way how these models learn over time, and excluding some of these data points, and we ended up really oversimplifying. So you can ask a lot of these questions, whatever you get from language models or generative foundation models, you start understanding what I'm talking about. So there are a lot of problems that we see, and then you can go on and on. But there is one fundamental problem also if you really go in neglected tropical diseases. Whole sort of undiscovered things. So you see a lot of these really affecting millions of billions of people, and there are no incentive for the farmers or for big tech companies to actually invest in these diseases. And traditionally, we start seeing they cause a health and economic burden to the majority of the population. And if you look at most of these actually affect 45% affect in low income, in particular in sub-Saharan Africa. So, right? So you see a lot of these, the neglected tropical diseases are responsible for over 200,000 deaths every year. It's significant, right? So now we know that global WHO and others put forward by 2022 or 2023, we have a target to eliminate this, but literally they are behind. And then they come up with a new target now by 2023. All right. So I'm not saying that there are not progress being made, but I think, are we really solving the right problem? And all this, what we see, I will consider most of the language models or the big foundation models are really addressing commercial problems as opposed to real problems, what we see today, right? So, and of course, the big challenge as you go really further, there is really a need a faster way to create, actually, if you cast this into the problem of really drug discovery problems, it start becoming interesting. Right, so can we discover new drugs? Can we intervene? And what does the drug pipeline look like? What is really the means and mechanisms? As you know, creating, producing, generating new drugs and get approval, it takes between 15 to 20 years, and with the cost of billions of dollars. And by the time things happen, there is a new kind of modality. So things are getting complex. So. But we started, the good news is that we started seeing organizations start matching some really goals. Right? How do you really accelerate? How do you now approach it from a different perspective, and in particular on achieving these targets? So I can go on and on, laying down the problem, the consequences, but I wanted to shift the gear. So the point I was trying to make is the world is not only LLM. So do you have all sorts of modalities. And we have all sorts of data sets. So, and we start seeing really a game being changed from in the world of pre-trained model, pre-trained representation from what we learn from these large models. They start changing the way the NLP world is changing, right? What does that mean if you look at actually in the chemistry, right? So the chemistry domain is really looking at you can cast most of the biological processes and the chemical processes and most of the chemistry and biology-related phenomena. You can cast them sort of from really understanding these are complex processes from a different angle. So at IBM, that's mostly we focus on IBM research addressing these kind of problems. What is really how do you actually come up with these large models from this context? How do you learn the chemistry? How do you learn the science behind this? And one thing we announced, I think it's already in a hugging phase, that is what we call the mole former, which is basically really a foundation model that really transforms specifically in the chemistry domain. And usually I keep hearing that you have to have these billions of parameters to achieve something larger. But the recent paper already demonstrated the smaller ones could do better than, or even comparable with a low cost and low carbon fruit at the same time. So this is one example that is a recent work we have been doing with Moderna. This context, really, it's interesting that it follows the same transformer-based approaches, a little bit of innovation from the representation perspective that actually allows you to do a number of really downstream tasks from generation perspective to property prediction perspective. And we have seen already it's outperforming a lot of these chemistry problems and helps. Actually, can see a couple of problems. We started long time ago, I would say 5 years ago, building on this kind of property. Maybe we have the expertise in house to do chemistry and chemistry and biological related problems. And then now we are also working on building this, what we call this biological foundation model, so what we call biomedical foundation model. So the goal here is really, how do we represent a human? So looking at from small molecules, biologics, to targets, right? And then you can actually unlock quite a number of downstream tasks. And what we see today is a small pie, all in the papers, but what does it mean really representing this compound human body complex interaction representation? And then you start now seeing a lot of really downstream tasks you can start exploring to do. So we started, it's a first version is going to come, and then you can feed from the patterns, from chemistry, from clinical data to biological data, molecules, and most of the data is already available. So, I mean, again, most of you know, right, from the biologics perspective, it really can treat them as a kind of a therapeutic kind of polymer property that really can mimic the organism actions that kind of evolve in immunology or signals and other biological contexts that can be represented using some already the techniques. And then that allows you to do a lot of these different types of tasks. And that's basically part of the drug discovery pipeline in general, right? And then from small molecule, for example, perspective, this T5 inspired architecture is basically encoder-decoder type of architecture. You could do actually this today, but it requires really clinical trial and in lab validations. It's not just generation. Once you generate, what do you do with that? So you have to go through the clinical process. The same thing if you look at from the small molecule perspective, that somehow a little broader perspective, and then how do you actually do that from that context? And that basically really beyond a specific modality, but it became more multimodal things that involves not only just building a model, models in this case not necessarily just from one data, but from different representation perspective, from the graph models to image, from smile strings perspective. How do you actually bring this and learn the interaction, the representation, and then you do all that of the generation properties. And then the most important thing is actually, yeah, you could do scientific studies, but how do you actually bring into real life applications also is a big challenge. And then if I just switch also the gear, we started seeing these foundation models generally start really changing the way we understand our planet Earth, right? So how do you actually take the analogy what we do from languages to geospatial data sets perspective that basically kind of start coming up in a way that changed the game. So recently we just announced a work that we have been doing with NASA, building this large foundation model that basically helps address 3 fundamental problems. One is basically looking at the disaster response problem perspective. Second, looking at from environmental climate change perspective. And then the third task to look around is basically data discovery perspective, basically exploiting all their instruments and satellite that NASA generates. And we started the journey, and a couple of family of models we already announced, and that basically start seeing really a revolution in some of downstream models, like a flood detection model. How many flood detection models you think that are available today? Thousands of thousands, and most of them are even bespoke really one time use. So we actually started using, start seeing a task that is on top of this geospatial foundation model for flood detection has shown 25% superiority across all the models available today. And a model being trained in Texas and the US was able to pick up across all the world. So these are the type of things we say a domain is important because whom we are talking about. And then you could do the same thing in fire scars detection. You could do land use, land change. You can use biodiversity monitoring. You can use carbon estimation. Then you go through nature-based carbon sequestration problems, on and on. So these are the type of the problems that we see from different modality perspective. But the question I have is really the potential of these LLMs and foundation models are really great in addressing fundamental problems we have seen in healthcare to come, and we start seeing some already. But there are critical barriers that we see if they are not addressed, really risk of leaving the entire low and middle income countries behind and actually benefiting from the advantage that we see today that really taken away them from even the planet from benefit perspective. And if you look at, for example, today, again, most of the speakers already said it, there is a limited access to high quality data, and most of these models are trained for those who have access to data. And we know most of you, I see a lot of familiar friends from Africa, and how people talk about data in Africa. But when you get the data literally 97% data is useless. And it comes with inconsistencies, partial bias, a lot of that is really incorporated, the way even the data being collected, even including the clinical trials that has been collected from instruments being tampered with. And then the whole problem in the skill gaps, from the domain from medical perspective, even from the technology perspective, skill gap. And ignore that what the previous speaker already said, the computational power is really absent. Just literally absent. Anyone talk to who is accessing a GPU today? So I'm happy to see the these what you call movies, I call them the quantum era, the blockchain era, and our language models era. And all of these actually excluded these communities. But the potential advantage, the potential benefit for these communities really immense than here. Here is more financial gain in the West, and there is basically really bringing people to the normal life. So the same thing we talk about is here we talk about bill care, there we talk about health care, right? That sort of analogy that from the technological looking at perspective you look at. And again, the context, we have seen a lot of progress in language models and how those language models really help in the contextualizing the challenge that helps 1, 2, 3 above, and a lot of things I didn't mention here. Of course, the other thing we talk about is ethical regulatory consideration that comes with security and privacy properties perspective is becoming a huge, huge, huge problem. And what are our call for actions to address this? I haven't heard a lot for the last couple of discussion. What are our actions to mitigate these kind of things? And I don't know what it could be. I mean, is there a way that we have this framework, something like this, with the ability of people to really come to bring you data and pick up the work? But today, what we talk about really models are commodities. Behind the models, all these the workflows, the tools, can we give access to those tools? Right? It's not the model. The model is commodity, can reproduce. But what are the tools to enable them to training, fine-tuning, inferencing, integrating into your workflows? Who is talking about these tools today? It's very, very important as we are talking just beyond models. What are the tools and services behind these models? So I'll stop here. If you have questions, I can go on, but I would like to stop here.
Fantastic talk. Any questions? So I have one. On the chemistry, set of slides, I thought that was really fascinating. And a foundation member of the AI task force has actually been digging into that as well. And I'm curious, how far along is that work? And have you identified any potential new markers that have been validated in the lab or through, any type of physical experiments?
Yes, we have generated the markers and the drugs, and the way we operate basically in validating is I work with partners. Maybe, as you know, our big partner in this space is Cleveland Clinic, right? So those are the people making us accountable, and all what we generate, they take into doing the testing in the wet lab. So that now, we're going that iteration. I couldn't publicly disclose, but that's the work we have been doing. So that's one. And also we do from the chemistry side, we have a lot of collaborators in Japan. Most of the chemical things happening. So I didn't mention there's one project we do what we call Project Rhizome, which is 10 by 10 by 10 by 10, 10 billion parameter, 10 billion data points, 10 billion something. It's going to come out. We started seeing really a lot of this discovery. So what we call accelerated discovery. How do you actually incorporate the discovery process along the generative processes? So that is where, and then we embed also simulation. There's another work I didn't mention we do with CERN, looking at the nuclear fusion as well. Yeah. Yes.
Yes, thank you so much for very interesting presentation. My name is Abel Wilson Walekwa, and I'm coming from Uganda. And just put the last slide you put in. And I was moved by the last slide.
This one?
The previous.
Or this? Oh, okay.
Okay, sorry about that. Yeah, but I was moved by those very pertinent and intriguing questions that you rose. I just wanted to also share that indeed those points are very, very critical. Sharing experience from Africa, they are really, really big challenge. But I just wanted to give some information that SASEMA, that is South African Center for Epidemiological Modeling Analysis in South Africa at Stellenbosch University, are trying to make a contribution in that. And they're trying to build capacity on the African continent, for example, for building these centers of excellences. But you raise a very pertinent point on the tools, on the behind the scenes, who is, what needs to be done. Those are very big issues, and I felt we could maybe brainstorm here and we see what to do. But also the other thing that came in my mind is if you've done some work and tried to dig on what available opportunities that we can leverage on to improve, for example, data quality. Of course, for me, that's what caught my attention mostly. Do you see some available opportunities that we could leverage on to improve data quality on the African continent? Yeah.
Yes. I think that's a deeper discussion we need to have. Yeah, data quality is something that so the way we capture data today, and there are tools, of course, improving the data quality perspective. I am a true believer that I don't need billions of data points. And we start showing today from the data quality perspective, I think one thing is, can we start from pre-trained model already? Because they may capture the generality, right? Then you come down to a fine-tuning specific model for the problem, the domain that we are interested in. That's where now the data quality start emerging labeling, right? So I think there are some tools already we can have a broader discussion on that. So one immediate thing is really the heavy lifting might be done already by the pre-built models already, right? So because the way you do these pre-built models are you have a car of any forms, but it doesn't have a Fiat or BMW format, right? So the BMW format is you're actually bringing on top of that one. So that's where the data quality improvement. I just simplified, right? So the base already learned from the car perspective. The car has a wheel, the car has that shape, this shape, that shape. But the specific car type that you do fine tuning. And for that fine tuning, if you don't have the quality data, which is a labeled small quality data, in the past you need thousands of billions of data points. Maybe today you need, like in the case of satellite image that I showed, to build a flood model, you need thousands of thousands. We showed 20 images for fine tuning could really show the same more or less equal performance accuracy with state-of-the-art model. So that's the area we need to start digging a little bit to start what really available from data quality perspective. The other data quality really is interesting to look at is, again, this we need to explore, using the simulation tools as a data generator, because that they bring you into the context, into the physics. And then you start now acquiring more data. So we can explore that. We have some ongoing discussion on that work as well.
Yeah, thanks so much. Really fascinating talk. I just want to leverage on the point that it just raised. I'm conscious that we have to move on to posters right now, but just a very small point. I was also fascinated by the point you mentioned about the quality of data. So I am based at the Wellcome Trust Center in Malawi, and we try as much as we can to produce very good data. But I was just amazed by the staggering thought you mentioned about 97% of the data is not accurate. How did you ascertain that?
Not accurate, rather accurate, userless. So I was.
Okay.
I'll give it. I couldn't mention names, but I was given 57 years of worth news data. 57 years worth of news data. And I couldn't make sense out of it because the data, the way it was archived, collected, missing, and it couldn't even connect the time and space even. So the way it was collected, the way it was stored, the way it's converted, fundamentally misguided in most of the cases. Okay? And the second case, if you look at some of the clinical data being collected, you have a partial information here, a partial information there. And they don't reconcile. There are some examples from medical, from healthcare perspective. And if you go to education, you see, I mean, don't quote me, I'm not by the name of IBM here, by the name of Kommy. And I can tell you stories after stories in all domains. I spent 7 years in Nairobi and digging this. And we learned all sort of this. Today, if you go in and get data from, let's say, Safaricom, literally the data is outdated. It's no use. Because the behavior changed. The way people interact, the way the people save, the way the people send changed. And what you have data point in time that couldn't even inform what is in the future to be predicted. So I can tell you more and more and more and more, but the point I was trying to make is that in some places where data being collected in a standard way, you can make sense out of it. But in many cases, these data are really silo and incomplete, inconsistent, corrupted. Did I answer your question? I don't want to break your heart, so I'm part of the problem.
I think this would be a great point. We could transition to coffee and the poster session. But first, I don't know how much energy people have in this room, but I am so excited. These have been great talks. I want to thank the speakers one more time. And I hope everybody's getting up that energy, or just go get the caffeine to help. But we have a poster session at 3:15. So if you go out these doors and kind of go down the hallway, you'll start to see all the wonderful posters. Please, stop by with all the presenters. It's going to be phenomenal. Thanks.